Oh hi! Hey there! Math time, statistics, probability, Unit 4.3, Binomial and Geometric Random Variables. Let's get started. First up, what is a binomial distribution? So, when the same chance process is repeated several times, we are typically interested in whether or not a particular outcome does or doesn't happen each time. Variables that count these are called binomial random variables. Now, when we refer to binomial random variables, it's important that we check to make sure that we have a binomial setting. A binomial setting arises when we perform several independent trials of the same chance process and record how many times a particular outcome occurred. There are 4 conditions to check to make sure we have a binomial setting. Those are that it is in fact binary, so the outcomes can be classified as either a success or a failure. That each trial is independent, so the trials must be independent from one another, meaning that if we know the result for one trial, it doesn't affect the result for another trial, which is a lot of things. We know the number of trials beforehand. We're not just doing it for an unspecified number of times or an infinite number of times. We know how many trials we're going to do. And then success. The probability for success is the same for each trial. So the probability of a successful occurrence over here isn't any different from the probability of success over here. The cute little anagram that you can remember this by is bins. You want to check the bin. If you have a binomial setting, then you will have these 4 settings. So if you want to check your bins. Now, binomial random variables. The count x of successes in a binomial setting is what we refer to as a binomial random variable. The probability distribution of x is a binomial distribution with parameters n and p, where n is the number of trials in the chance process and p is the probability of success for any one trial. And the possible values of x are the whole numbers from 0 to n. So x is going to be a series of whole numbers, right? It's not going to be decimals. And basically how many times you are successful is the variable. For example, if I'm going to toss a coin a certain number of times, let's say 5 times. So each toss is going to land on either heads or tails. And knowing the outcome of the first toss doesn't affect the second toss. So therefore it is binomial and it is independent. If we define landing on heads as a success, then the probability of success of landing on heads is 0.5 in any one toss. And since I said that we're doing it 5 times, then we also know the number. So it's binomial, it's independent, we know the number of trials, and the probability of success is the same for each trial. So we have our bins. Therefore, this is a binomial random variable where the number of times we successfully have the coin land on heads is our binomial random variable. So we can set up a binomial distribution for this setting. Now, binomial distributions can either be discrete or continuous, just like random variables from before. So for discrete probabilities, often we will be interested in the probability that x equals k. So the probability that x, our number of successes, equals a specific number. So, for example, let's say each child has a probability of 0.25 of having type O blood. If the parents have 5 children, then the count of x is the number of children with type O blood, and that is a binomial random variable with n equals 5 and p equals 0.25. So each individual child is, a binary, either they have type O or they don't have type O blood. Each child is independent from the previous one. We know how many children they have 5 children, and the probability of success for each of these children is 0.25. So then we can ask the question, what is the probability that x equals 2? Which translates to, what is the probability that 2 of the kids have type O blood? So to figure this out, first we have to find the probability that x equals 2 in general. So the probability that we have 2 successes and 3 failures. It seems a bit harsh to call a kid a failure. In this case, a failure is not having type O blood. If we're trying to find the probability that 2 kids have type O blood, we have to find 2 kids with type O and 3 kids with something else. So since the probability of having type O blood is 0.25, then we have the 2 kids with type O blood, so 0.25 times 0.25, and then the 3 kids without, so 0.75 times 0.75 times 0.75. Quick math will show you that that equals 0.026. So now we have to count the number of ways that x can equal 2. This is the probability that specifically the first 2 kids have type O blood, but it could be You know, the first two kids, the first and third, the first and fourth, the first and fifth, the second and third, the second and fourth, the second and the fifth, the third and the fourth, the third and the fifth, or the fourth and the fifth. So count all these up, there are 10 different ways 2 of the kids can have type O blood. So then what we have to do is take our 0.027, or 0.026 rather, and multiply it by 10, since there's 10 different ways it can, 2 kids with type O blood. When we do that, we see that the probability is 0.26, so just over a 25% chance. Now, if you don't remember how to go through that process, it's okay. There's a formula for you. Of course there is. So if X has the binomial distribution with n number of trials, and probability of P success on any individual trial, and K is the number of successes you're interested in, then the formula we can follow is as follows. The probability that X equals K equals n choose K times P to the K power times 1 minus P to the n minus K power. Now that looks a lot more complicated than it is. N choose K is fancy talk for the number of ways we can get K successes, right? So before, n choose K was the number of ways we can get 2 successes, right? There were 10 different ways. So n choose K in that setting, 5 choose 2 equals 10, right? And there's a function in the calculator that'll do this for you, right? The probability of success, P, is usually given to you in the problem. In the last case, that was 0.25. And the number of successes, K, is also given to you in the problem. In the last case, it was 2. So this would be 0.25 to the second power, and then 1 minus 0.25 would be 0.75, so this would be 0.75 to the third power, since 5 minus 2 would be 3. So this would be 10 times 0.25 squared times 0.75 cubed, right? That's not really that complicated of a formula, it just looks a lot scarier when we first look at it. So now that we understand that formula, we can think about what it would look like if we were going to try to use that same formula to go further. So back to the previous example, what is the probability that exactly 3 of the children have type O blood? Use the formula that we just saw to find the stated probability. So again, basically we're pulling in 3 for K. The P is still 0.25, and 1 minus P is 0.75. So this becomes 10 choose 3, which we'll get to. But 0.25 to the third power times 1 minus 0.25 to the second power. Now, n choose K, again, it'll be available on most of the formulas, but it can be found easily by doing n factorial divided by K factorial times n minus K factorial. So basically this is 5 factorial divided by 3 factorial times 2 factorial. Factorials, if you don't remember from, I don't know when you would have seen them, basically it's the integer that is on the factorial times every integer down to 1 that comes before it. So and 5 factorial would be 5 times 4 times 3 times 2 times 1. Obviously you don't multiply times 0. 3 factorial is just 3 times 2 times 1, and 2 factorial is 2 times 1. So n factorial would be 120. 3 factorial would be 6, and 2 factorial would just be 2. So 120 divided by 6 times 2, so 120 divided by 12 would be 10. So this is 10 times 0.25 to the third power times 0.75 to the second power, which when you do the math equals 0.087. Now, should the parents be surprised if more than 3 of their children have type O blood? Well, to do this, we would have to know the probability of 3 children having type O blood, 4 children having type O blood, and 5 children having type O blood. There's a way to do, we could repeat that formula over and over again, but I want to show you how to do it in the calculator as well. So we know it's a binomial, right? Well, if we look at our probability tab under distributions, well, first of all, we have factorials, so we can do factorials pretty easily. You can also just use the exclamation point. But for distributions, one of our binomials, we have binomial PDF and a binomial CDF. So for a binomial PDF, that is if we want to know the probability that it is any one value, if x equals a specific k. So if I want to know the probability that x equals 3 in our last example, I could do the total number of trials, the probability of success, which in this case was 0.25, and then a specific x value, in our case, would be 3, and we see the 0.0878 that we had before. Now, one thing to note, if I want to know all of them, then what I can do is the exact same thing, but I can leave this part blank, and it will tell me all of the probabilities as we go along. So the probability that none of the kids have type O blood is 0.237. Probability that one kid has type O is this, then this is 2 kids, and this is 3 kids, and then I can keep going and get 4 kids and 5 kids. So one way to answer our question is to just add this value plus this value plus this value together. Another way we could do it, if we want, is to use a binomial CDF, which is the option right underneath it. So if I want, I can do the exact same thing, but I want to know the probability that it is 3 or more children have type O blood. So in this case, my lower bound would be 3 and my upper bound would be 5, because the most is 5, right? And that would be the same as if I went through and added each of these 3 probabilities together. I would get the same amount. So if you want between this and another value, then that would be the way to go about doing it. So to answer the question, should the parents be surprised if more than 3 of their children have type O blood? Well, there's a 10% chance, so maybe a little bit surprised, but it's not really outside the realm of possibility. Something that is 10% possible means 1 out of every 10 times it's probably going to happen, right? So, I don't know, probably not. They shouldn't be that surprised. A little bit surprised, but how we've defined it in the past, that's not really outside the realm. All right, so for a binomial distribution, it has certain properties, right? First, the mean. Mean is very easy to find. If you want to find the mean for a binomial, n times p. That's it. Number of trials times probability of success on each trial. That's it. That's the thing. That's how you find the mean. For standard deviation, it's the square root of n times p times 1 minus p. I couldn't figure out how to make the square root symbol go over the whole thing here, so all of this would be under the square root. It's not just the square root of it. It's the square root of this whole thing. If we're asked to describe the shape of it, well, we use the same properties as we've done before, same descriptors as before. Probability distribution of x is, in this case, skewed to the right, with a higher probability of having 0, 1, or 2 children with type O blood than any larger value. Pretty straightforward stuff, right? Now, when is it appropriate to do something like this? So in the real world, when we take samples, we do it without replacement, okay? We learned early on in class that when we take samples without replacement, it means that the probability is going to change from trial to trial, right? If I have a bag of 10 marbles in it, 6 of them are blue and 4 of them are red, and I want to know the probability of drawing a blue marble, well, if I take a blue marble out, or if I take a red marble out, and I don't put it back in the bag, then the next time I draw a marble out, it's going to change the probability. So, obviously, in these circumstances, we can never be 100% precise, right? It's just probability, because most of the time, we're not going to be exact. We will be close, and for us, close is close enough. So the rule that we use to justify the use of our formulas that we're using is that if the sample is at most 10% of the population, then we can use binomial distributions to describe populations. So if we have a situation where we're asked to use a sample to describe a population, since our sample is, as long as our sample isn't more than 10% of our population, then we're not going to change the probability of any one trial enough to notice. So the rule of thumb here is that the sample should be less than 1/10 of the population at most. Now, for us, if we need to, then as long as n, our sample size, is big enough, more than 10, or I'm sorry, not more than 10. Big enough in this case meaning we have at least 10 successes and 10 failures, then we are allowed to approximate the binomial distribution to a normal distribution. So if that's the case, then we can use our normal curve to give us values like, the probability between values. Like if we're using a continuous setting, right? So if I want to know the probability of between 10 and 40 successes out of 50 trials, I can use a normal curve to approximate. Now, the thing is, we all have TI Inspires, or at least are allowed to use them now, so we don't have to approximate if we don't want to. Well, we can literally use the normal CDF or the binomial CDF like we did here. It does it for us. If we approximated using a normal, we would, in most cases, we would get something that approximates very closely. However, the binomial setting, if we're able to use it, is going to be more precise for a binomial setting. So we should use it. So there you go. So for our purposes, we can just use the binomial. We don't have to justify using a normal CDF in a binomial setting because we have a binomial setting on our calculator. It used to be the case that you didn't have that option, right? All right, so very quickly, we're going to talk about geometric distributions. So geometric distributions, they sound fancy. They're not. A geometric setting arises when you perform independent trials of the same chance process and record how long it takes you to get your first success, right? When you're asking the question, what is the probability that the first time this outcome happens is X, right? Like how long, what's the probability that it's going to take 5 coin flips for me to get my first landing on heads, right? That is a geometric style question. So we use Y for number of trials for a geometric. That's just common practice. The probability distribution of Y is going to be a geometric distribution with a parameter P, which is the probability of success on any trial. We don't have an N, we don't have a specified N in this case because we don't know how long it's going to take for our first success. That's sort of the premise of the question. We're not supposed to know. We're asking what is the probability that my first success will happen on blank, right? So the probability of success is this. The random variable Y is going to be what we're looking for, and it's the probability of it being 1, 2, or 3 or whatever is going to change, however, depending on the situation, right? The formula is very similar to what it looks like for a binomial with some slight changes, right? So if Y is a geometric distribution, the probability that Y equals any given K is 1 minus P to the power of K minus 1 times P. So in the case of the coin flip, well, no, I don't like that. If we're going to do the type O blood thing, right? The probability that the third child is the first one that has type O blood. What this is saying is that the first 2 don't, and then the third one will, right? So 0.75 times 0.75, all right, so K is 3 in this case, so 0.75 to the second power times 0.25. If we want to know what's the probability that the 10th child is the first one that has type O blood, then it would be 0.75 to the 9th power, so 9 failures, and then the 10th one is a success. So it's the probability of failure times how many failures you're looking at, then the last one being successful. That's how we can interpret this formula. How to describe it? They all look like this, right? The probability that happens on the first one is going to be the biggest one, and then the further down you go, the less likely it's going to be, right? So the mean, or the expected value, is very easy. It's just 1 over the probability. Whatever the probability is, 1 divided by that. Done. The standard deviation is the mean times 1 minus the mean. I know that seems weird, but that's just how you do these. They are technically infinite. They never end. Technically, these can go on indefinitely. So it doesn't make sense to describe a range because the range is always going to be to infinity. It is heavily right skewed, and the most likely value is 1, but like you're not going to be asked to describe the shape of geometrics. They all look the same. And yeah, that's geometric distributions. A lot easier than binomials, but we also don't really spend a whole lot of time on them because they don't really come up that often. So yeah, I wouldn't stress about them too much. Anyway, that's everything about binomial and geometric distributions. I hope this was helpful.